Hello good people and welcome back, and this is unit 6, and in this unit we are talking about interest rates. In our last video we stopped here when we're talking about zero rate, and we said that a zero rate for a maturity T is the rate of interest earned on an investment that provides that provides a payoff only at time T. And we made a contrast between the zero rate that considers no payment as made within this period versus that's no payment is made within this period here versus a return on a bond that actually does pay coupon for a period of time. Now, the traditional derivative instrument that we look at are futures, forward, swaps, and option. And for all of those instruments, the characteristics that they have that they share is this idea that the agreement is entered into today and the transaction occurs in the future. In the future here we have a payoff. And so in order to find the value today of that payoff, we're going to be using the zero rates rather than using, say, a yield to maturity on this investment that accounts for the reinvesting of this coupon that they received. And that is the difference there. Now, to understand that even better, we're going to work with an example, and the example that we're going to work with is an example with bond pricing. And we're going to use a zero curve to value the bond. So let's look at the zero curve that we have. The zero curve that we have here essentially says that we're going to use a discount rate of 5% for a maturity of half a year, a discount rate of 5.8% for a maturity of 1 year, discount rate of 6.4% for a maturity of 1.5 years, and a discount rate of 6.8% for maturity of 2 years. So what does that mean for us? I'm going to try to copy that data over here really quick, and then I'm going to get back to this so that we can continue with our rate. So the maturities are as follows. We have the years here, and we have 0.5 years, we have 1 year, 1.5 years, and then we have 2 years. These are the maturities that we have. It's going to be 1.5, and this is going to be 2 years. All right, and the zeros are going to be as follows. We're going to have 5% here. We're going to have 5.8%. We're going to have 6.4%, and then we have 6.8%. Those are the maturities. What does that? Do this mean? It means that the discount rate that we're going to be using for a zero coupon investment starting today in that last half a year would be 5%. A discount rate for a zero coupon bond that starts today and that expires in a year is going to be 5.8%. So to do that, let's consider an example. We have a 2 years. We have a 2 years coupon paying bond that pays interest semi-annually. Semi-annual interest, and with the semi-annual interest, we also have something that we also have is the coupon payment. I'm going to say interest here, and the coupon rate is going to be equal to 6%. The face value of this bond is going to be equal to the traditional 100 or 1,000, depending on how you want to structure it. So if we have a face value at $100, a 2 years bond, 6% coupon, what is the price of this bond? Well, if you were to use your financial calculator the way you used to do, what you would do, you would say, well, the price of the bond is going to be equal to To find the price of a bond, you would essentially do the following. N is going to be 2 times 2, because 2 years semi-annual, right? That's going to be equal to 4. Then you're going to need the payment, and the payment is going to be equal to the coupon payment, which is equal to face value, that's 100, multiplied by coupon rate, which is 6%, divided by 2, because it's semi-annual, so you're going to have 6 divided by 2, so you're going to have 3. The future value of this bond is going to be equal to face value, that's going to be 100. But then you're going to need a third component. You're going to need a yield to maturity, or IY. And in this case, you do not have IY here. And how do you value this bond in the event where you don't have that yield to maturity? Well, to do that, you would use a zero curve. And that zero curve would essentially look something like this. We would have first half a year, we'll have 1 year here, 1.5 years, and then we'll have 2 years. So I may be redoing this like that. There we go. Now, at each point, we are receiving coupon payment, and our coupon payment we found out is $3. So we're going to say 3 here, 3 here, 3 here, and 3 here. And at maturity, we're also receiving 100. So we're also going to receive 100 here. So the total last payment that we're receiving is going to be at 103. That's what we're getting there. The next step for us is going to be to recognize what are the periods that are matched to each zero. Well, we can essentially break down this payment as follows. Instead of having essentially one coupon paying bond, we can strip the coupon paying bond into 4 different zero coupon bond. And so we could say that this first payment really is just one unique zero coupon bond that matures in half a year, and that pays you $3. And the interest rate that you're going to use to discount this, is going to be the equivalent of the zero bond for the zero for that period. So that interest rate is going to be at 5%. It's going to be 5% annually, right? So it's 5% of times t, which is that 1/2. So it's going to be 5% that you're going to use here. That second cash flow is essentially going to be the same. So the second cash flow is going to start here. That becomes another 0, right? Where we receive $3 here, and we are discounting at this rate, which is 5.8%. So we're discounting that at 5.8%. And then we do the same thing for the third one. The third one is going to start here. It's going to mature here. We're still going to get $3. And the discount rate that we're going to use there is going to be the 6.4%. So it's going to be 6.4%. Now, T here, or the expiration is going to be 1, is going to be 1.5 here. And our last one is going to be the same. So the last one is going to start here and it's going to expire here. And so we're going to have 2 years. Our cash flow is going to be equal to 103. That's the 103 that we have here. And our discount rate is going to be 6.8%. And so if we were to do just that, we could, remember these are continuously compounded interest rate, those are the zeros, we could find the present value of each one of these cash flows and just add them up to find the price of this zero coupon bond without needing to find the yield to maturity. And so what we would do is essentially find the present value of each one of those, and that would be computed as follows. $3, that's going to be the first one here. I'm just going to label that 2, 3, and 4. The first one is going to be $3. To find the present value, we remember that to find the present value, this is what we do. We did. I'm going to shrink that a little bit. To find the present value, this is what we did, right? We say present value is equal to future value, exponential minus continuous compounded interest rate multiplied by t. So this is what we apply here. That's going to be future value because we're getting that at some point in the future. Exponential of minus the 5% multiplied by t, which is 1/2. And so that is the first cash flow. The second cash flow is going to be $3 exponential of minus 5.8% multiplied by t, which is 1, plus the third cash flow, which is $3, multiplied by the exponential of minus 6.4% multiplied by t, which is 1.5. And then the last cash flow is going to be equal to 103 multiplied by the exponential of minus 6.8% raised to the power of 2 multiplied by 2, which is t. And the sum of all of this will give me the price of this bond. And it turns out that that sum is exactly equal to, if you solve this, that sum is going to be equal to 900 or 98.39. That would be the price of that bond. Now, we didn't need to find the yield to maturity on the bond, because without the yield to maturity on the bond, you cannot find the price of this bond, right? And without the price, you cannot find the yield to maturity. So in order to do that, we're going to strip the bond into 4 different zero coupon bonds, and then find the present value of each one of the payments that are using the zero curve, and infer the price of the bond that way. Now, that's what we would do. And then so if we go back to our slides, that's exactly how we would use the zero right there. And so for our bond pricing, which is the example that we just worked in here, to find the price of a bond without needing to find the yield to maturity in the bond, we're going to discount each one of the cash flows at the appropriate zero rate. How do we find the appropriate zero rate? We have to strip the bonds. Just to find the proper zero rate to match to the period, we're going to go back here and we're going to do this. We're going to strip the bond for the first period, and that is maturity of half a year. So we go back to our table and we read the coupon that matches half a year, and that's 5%. We read the interest rate, the zero rate that matches half a year, and that's 5%, and that's why we use 5% here. And we do that for every single one of those cash flows in order to find the price of that bond. Okay. So in our example, which is what we just did there, the theoretical price of the bond with the 2 years to maturity provided 6% coupon semi-annual is going to be the $3 that you're getting for the first payment in half a year. Exponential of minus 5%, t is 1/2, $3. Exponential of minus 5.8%, t is 1 there, plus $3 exponential of minus 6.4%, t is 1.5. And the last cash flow has a face value in it. That's why it's 103 exponential of minus 6.8% multiplied by 2. That's how we get the 98.39. Now, how do you go about finding the yield to maturity on the bond? Right? To find the yield to maturity on the bond, you use the zero curve, which is this curve here. We use the zero curve, which is this matching of zeros and maturity, in order to find the price of the bond. So now we found the price of this bond. The next question is, how do you go about finding the yield? Well, to find the yield, what you would do is you set the present value of the cash flows equal to the price of the bond that you just found out. Now, in our example here, what do? What the yield to maturity is going to be that constant rate that you use in order to discount the cash flows, so that the present value of the cash flows is equal to the price of the bond. So you would simply remove each one of these yields here, and instead of having different rates here, you will set that equal to a y, which is the yield to maturity. And therefore, what do we have? In that case, we're going to have 3 exponential of minus y, which is the yield to maturity, multiplied by 1/2, plus 3 exponential of minus y again, which is the yield to maturity, multiply this time by 1, plus 3 exponential of minus y, multiply this time by 1.5, plus 103 exponential of minus y, again, multiply this time by 2. And this is the yield to maturity, right? So if we use the same yield for every time horizon, that allows for us to have that continuously compounded return on our investment. And so the price of this has to match the price of the bond, and that price of the bond we found out will have to be equal to the 98.39. And so the goal would be solve for y. Now, doing this is a little tedious, so you have to use something like a calculator, a solver in Excel, or a goal seek. In Excel as well, in order to solve for this yield to maturity. All right, so that is essentially what we have. That's essentially what we have here. The bond yield is a discount rate that makes the present value of cash flow on the bond equal to its market price, or equal to its price. So now, if you suppose that the market price of the bond is the same as the one that we had in our example, which was 98.39, that early example that we solved, what is the bond yield that makes that present value of all those cash flows equal to the price of the bond? Well, remember, the bond yield is that constant rate. That's why we have the same y here, so that the present value of the cash flows, which is this entire expression, is equal to the price of the bond that we found early. And that is the definition of a bond yield. That is the discount rate that makes the present value of the cash flow on the bond equal to the market price of the bond. And so you would solve this to find the yield. In this case, you'll find the yield at 6.776%. Now, another concern you may have with respect to this is, what if we have a price set? What if the price is set and the price we know is going to be at $100? We also know that the discount rate is going to be the discount rate for each period is going to match what we have with respect to our zero curve. So instead of looking at it here, maybe we want to look at it in the earlier slide here. So what if we know that the price is going to be at let's say we know that this price is going to be equal to 100, is going to be equal to the face value of the bond at 100. The question is, given this zero curve that we've been using here, which is those rates here, what should be the appropriate coupon payment? And that's what we're looking at when we talk about the par yield. Well, the par yield, in this case, for a certain maturity, for a given maturity, is a coupon rate that causes the price of the bond to equal to its face value. So given the price of the bond that's equal to the face value of the bond, the question becomes, what kind of coupon rate should we use given given the use of the zero curve, so that the present value of those cash flows is equal to the price of the bond? And if we did that, we would essentially set up this expression as follows, where the coupon, remember, if we go back to our board here, what we had in this example here, what we have is $3. And what was $3? The $3 we found out to be coupon rate multiplied by face value, which is 100, divided by 2. That is essentially what we use, right? So the coupon rate, which was 6%, that's what we had, multiplied by 100 face value divided by 2. So the coupon payment for the year was, let's say that coupon payment, which is 6% divided by 2, multiplied by 1,000, let's call that C, and we're going to divide that by 2. So every time we have 3, we know that that's C divided by 2. And so let's rewrite this. That's going to be, instead of 3, we're going to say C divided by 2, and then we're going to discount that at the appropriate zero rate. The zero rate for half a year, remember, was 5%. So it's going to be minus 5%, 1/2. Right? We are given the zero rate. We want to find the coupon rate that matches that. And so the second one would be C divided by 2. And then we're going to see exponential of the same thing. The zero for the 1 year is going to be minus, what was that, 5.8% multiplied by 1 plus c divided by 2, and then we're going to do exponential of minus 6.4% multiplied by 1.5, and then the last one is going to be 103. 103 was 100, which is face value, plus the coupon payment, which is c divided by 2, that we now discount at minus 6.8% multiplied by 2. We want this cash flow to be equal to the par value of the bond, which is 100. So when we set that up equal to this, what we're going to have is the following. We're going to have 100 is going to be equal to c divided by 2 multiplied by the sum of these exponentials, 5%, 1/2, plus exponential of minus 5.8%, multiplied by 1, plus the exponential of minus 6.4% multiplied by 1.5, and we're also going to add this last component plus the exponential of minus 6.8% multiplied by 2. That is that plus the present value of 100, so that's going to be $100, and then multiply minus 6.8% multiplied by 2. So we can simplify this even further by moving this expression over here, right? Because we want to find c. That's what we are after. So if we did that, we would have 100 minus 100 exponential of minus 6.8% multiplied by 2, multiply all of that by 2, and then what I'm going to do is, and that's going to be equal to c multiplied by this whole term here, right? That's sum of the exponential. That's sum of, I'm just going to rewrite it all. Exponential of minus 5%, 1/2, plus exponential of minus 5.8%, plus the exponential of minus 6.4%, 1.5, plus the exponential of minus 6.8% times 2. And so c can be found using the ratio of those two. So it's going to be 100 minus 100 exponential of minus 6.8% times 2 divided by the sum of those exponentials. So let's call this whole term here, let's call that whole term a. If this whole term here is a, we're going to divide that by a. So what do we have? C is going to be equal to 100. Let's call this term something else. Let's call this term here, well, it's going to be equal to 100 minus 100 exponential of minus 6.8% times 2 divided by a. That's what our coupon rate is going to be. Our coupon payment is going to be. Now we can simplify this even further. You don't have to do this math every time. This is a formula that does that for us. In that formula, it turns out, and that's exactly what we do here, right? We set up this c divided by 2, and then we add them up, and we solve for the coupon rate here. Now, the formula that solves that for us is fairly straightforward. That's that coupon rate here, that coupon payment here, or coupon rate, is going to be equal to 100 minus 100 multiplied by d multiplied by m divided by a. Now, what is d, what is m, and what is a? M is the number of compound. M here is going to be equal to the number of compound payment per year, so the number of compounding period. And also semi-annual problem, so M is going to be equal to 2. D is the present value of $1 received at maturity, and A is going to be the present value of an annuity of $1 on each of the coupon date. So in a sense, what do we have? We have D is going to be the present value of $1 received at maturity. So the present value $1, present value received at maturity. Maturity is in 2 years, and the rate of return that we use at maturity is going to be equal to the 6.8. That's the 6.8%. So we're going to do that $1 exponential of minus 6.8%. T is equal to 2 there, right? That's what we have, and we are going to, that's what we're going to use there. That's D. That's what D is going to be equal to, and A is going to be equal to the present value of an annuity of $1 for each one of the coupon date. So what do we have? What we have here at the end is A is going to be the present value of an annuity. So it's going to be 1 present value minus 1 minus, that is, it says here, an annuity of $1 on each of the coupon dates. We have 4 coupon dates, right? So our coupon dates are going to be the following: half a year, 1 year, 1.5, and 2 years. And we're going to have 5, 5.8, 6.4, and 6.8. So that gives us the present value here of $1 for the first one, which is 5% at half a year, plus the present value of $1 at 5.8% for 1 year, plus the present value of $1 minus 6.4% for 1.5 years, plus the present value of $1 at minus 6.8% for 2 years. This is what A is going to be. And so if we go back to our board, that's essentially what we have. Oh, here I actually forgot the 2 here. It should be here. That's the 2 there, right? So what do we have? We call this, in this scenario, we call this term here as D. We call that M, and we call this A. So our coupon is going to be equal to 100 minus 100 multiplied by D, and we know what D is, multiplied by M, we know what M is, divided by A. And that's the formula that you should be using. Alright, so let's go back to our, and you remember, see here, A is exactly the same as what we have, where we have just the sum of the present values factor for 1. And so if we go back here, this is what we call A, right? And A was the present value of those sums. So A was these terms that we have here. This was A that we have here. All right. So far, what we've been able to do is essentially build from the intuition that we had earlier, that the coupon payment can be split into, can be essentially stripped into a series of zero coupon bond, and that's what we had all the way here, right? Where we essentially stripped this payment. We essentially strip this series of cash flows here into zeros, a series of zeros. And we were able to use the zeros, or the zero rates, in order to find, one, the price of the bond. We were able to use the price of the bond that we obtained. And remember, the zero rate was, each cash flow was discounted at the zero rate for its maturity. That cash was discounted at 0 for its maturity, and so on and so forth. And the sum of these present values was equal to the price of the bond. Now we use the price of the bond in order to compute the yield to maturity on the bond, and we said that to do that we would set this up to be true, and we would use something like Excel solver or GoalSeek to solve for that. And then we said, well, what if the organization wanted to sell the bond at par value? If the organization wanted to sell the bond at par value, and they were to use the zero yield in order to value to estimate what the coupon payment should be, how would they go about doing that? We said, well, in the previous scenario, the coupon payments here was equal to the coupon rate, that is 6% multiplied by face value divided by 2. So let's call this 6% multiplied by face value C, and let's try to solve for it. And so when we did, we essentially found a coupon formula, and that coupon rate formula or coupon payment formula was equal to the following. It was equal to 100 minus 100 multiplied by D multiplied by M, which is number of compounding period, divided by A, and A was this present value factor, which is the sum of all of these present values of a dollar. Now I'm repeating this here because we're going to be using this here in a second. This process all rely on the fact that we have a given table for our zeros. All that relies on the fact that you have this table. And so what we're going to do next is coming up with this zero table. Now, we want to remember that the zero table that we have here is made of continuously compounded rates, right? So all of these are continuously compounded rate, and that's the key here. That's what we want to remember. So the way we're going to go about creating or estimating this zero curve is by looking at the current market value of some of the zero coupon bonds that are trading out there. I'm going to pause for a second and stop for the phone there. Alright, sorry about phone ringing there. I had to pause for a second to get that phone out of the way. So now the goal that the objective is going to be to estimate this zero curve. And the way we're going to do that is by using a method that's called bootstrap. And the bootstrap method, what it does is it uses outstanding bonds. Those are bonds that are currently trading. It uses their market value to zero coupon bonds or coupon paying bonds given their maturity in order to infer the appropriate zero rate for the period. And so the way we're going to go about doing that is using an example that we have on our slides. And so that's what we're going to do next. We're going to be finding the zero curve or building the zero curve. And we're going to use this information that we have here. The information that we have in front of us here is current bond prices. So we have a bond that is currently selling for $97.5. It has a face value at 100 and it matures in a quarter. So what this means for us is that this bond has as follows. It matures, I'm just going to make it a little shorter than that. So it matures in a quarter, and that is going to be 1/4. That is a quarter, right? It matures in 0.25 years. It has a face value of 100, which means the payment here is going to be $100, and it has zero coupon. So it's a zero coupon bond. There's no payment that's due between these two periods. And the current price of this bond is at 97.5. So we're going to say 97.5 here. And so what we know de facto, given what we've learned so far, is that the price of this bond is the present value of face value using the continuously compounded interest rate. So what does that mean? It means that the zero, so if we could say 0 here if we say our zero curve or our zero rate would be filled in this table here. Now our zero rate for a maturity of 0.25 would be the interest rate, the continuously compounded interest rate that would grow $97.25 into $100 in 0.25 years. So to find the zero rate, what we're going to do is we're going to say that $100 is equal to 97, or let's put it the other way, $97.5, which is the price of the bond, is equal to the present value of face value, which is $100. Present value is exponential of minus continuously compounded rate, that's RC, to multiply by t, which is time, which is 1/4, right? And so we can solve for the continuously compounded rate. And the way we're going to solve for the continuously compounded rate is by dividing both sides by 100. So that's going to be 97.5 divided by 100. is equal to the exponential of minus continuously compounded rate divided by 4. Let's multiply by 1/4. And then to find the continuously compounded rate, which is this value here, what we're going to do is we're going to take the log of both sides, right? And so our continuously compounded rate is going to be equal to minus the log of the ratio of the price divided by the face value multiplied by m. And m here is 4 because 0.25 is a quarter, so that's 1/4, and m is 4 for the quarter. And so what we're going to have here is going to be the log of minus the log of 97.5 divided by 100 multiplied by 4. And so let's pull our financial calculator and let's do just that. 97.5 divided by 100 equal, we take the log of that minus multiply by 4. That gives us 0.12127, so that's times 100. That gives us 10.1271%. So it's going to be 10.1217%. That would be our zero rate for a quarter. Then we would do that same for every single one of these zero periods. So I'm going to go back to the board and redo this on the board so that it is clear. And in order to do that, I'm going to copy this information over to the board. Okay, so let's do this. I'm going to clear this up. Here. And what I'm going to do is I'm going to pause for a second, copy that information, and bring it back to the board. All right, so I copied and pasted the data here, and we can go ahead and create our zero curve from this data. Now we know already what the process is like based on the work that we just did on the PowerPoint. So here, what we're going to do is we're going to create a zero curve using that same process. Okay. We're going to work with the maturity, and essentially what we're going to do is we're going to start with the first one. The first one has a maturity which is equal to 0.25 years, which is also 1/4 of a year, right? 1/4 of a year. And so what we have with that maturity is the following. A bond is trading here, is selling here, and it has a maturity of 1/4 of a year, and face value, which is 100, is going to be paid at the maturity, and the current price of the bond is at 997.5. So 97.5 is the current price of the bond. So what we're going to do is we're going to set up our equation, and our equation is going to be essentially the following. It is going to be setting up the price of the bond is equal to the present value, the price of the bond, which is that, is equal to the present value of this, of the $100 at the zero rate. And so what we're going to have is the following. We could do it one of two ways. We could say 97.5 is equal to 100. I may use a different, give me just a second here. I want to use a slightly bigger, maybe 97.5, that's a lot better, is equal to 100, that we multiply by the exponential of minus the continuously compounded rate that we're after, multiplied by t. Now, that zero rate that we're getting here, this value here, which is the zero rate that we're after, is essentially, that value here is essentially the zero rate for this maturity of 0.25 years. So to find that zero rate, what we're going to do is we're going to say 97.5 97.5 divided by 100 is going to be equal to the exponential of minus the 0 rate multiplied by t. And so if we take the log of both sides, that's going to be the log of 97.5 divided by 100, and that is going to give us, it gets rid of the e there, so it can give us the minus the realized compound rate, or the compound right here, multiplied by t. So the compound rate, and that is for a maturity t of 0.25, 0.25 is going to be equal to minus the log of 97.5 divided by 100, and then what we're going to have in this case is we're going to multiply that by t. Now remember that t in this case, we're going to divide by t, which is divide by t, but you know that t is 1/4, right? And so that's what t is. Let's just plug in the values. So if t is 1/4, that is going to be, realized compound rate is going to be minus the log of 97.5 divided by 100 divided by 1 over m. M is 4 because we are working with a quarter. So our realized compound rate is going to be equal to minus the log of, if we generalize this value that we have here is the price, that's the face value. So it's going to be log of minus the log of the price divided by face value, and then we're going to multiply by m. Because when you divide by 1 over m here, you might as well multiply by m. And so that's essentially what we're going to have. Now, for t is equal to 0.25, what we have is the 0 is going to be equal to minus the log of, the price at that point is 97.5 divided by 100 multiplied by 4, because that's the quarter. The t is equal to 0.5. The 0 there is going to be equal to minus the log of, the price there is going to be, I'm going to use it a little thicker there. There we go. The price there is going to be that value, 94.9. So it's going to be 94.9 divided by 100, because it's the same face value. Multiply this time by t is 1/2, so it's going to be 1 over 2 is 1 over m, so m is 2 multiplied by 2. And so if t, for the third one, t is equal to 1, what do we have? The 0 is going to be equal to minus the log of, the price here is 90 divided by 100 multiplied by 1, because this is going to be 1 over 1. That's 1 year. Okay, so the first scenario gives us what? The first one gives us, I think that's what we did earlier, 97.5 divided by 100 equal, we take the log of that, we remove the negative sign, and we multiply by 4. So that's 10.127. 10.127%. That is our first 0. Our second 0 is going to be equal to 94.9 divided by 100 equal, and then we take the log of that, we remove the negative sign, and we multiply this time by 2. That gives us 10.469, so it's going to be 10.469%. And then the last one, which is this last one here with the 0. So far we are only working with the 0 because this formula applies for the 0. What we're going to do is the log of, that's 90 divided by 100 equal, we take the log of that, we remove the negative sign, and we multiply by 1. That is multiplied by 1, so no change. So it's going to be 10.536. So 10.536%. So these are going to be our zero rate. So if we are to expand and start building our zero table is going to be something like this. For t at 0.25, the 0 is going to be 10.127%. For t at 0.5, the 0 is going to be at 10.469%. And for t is equal to 1, our 0 is going to be 10.536%. That's what we have so far, but we're not done, right? Because we still have these last two components here. The 1.5 years, which is that one, and the 2 years, which is that one. So let's do the same thing for the 1.5 and the 2. For the 1.5, we are receiving a coupon, so it's not a zero coupon. For the 1.5, we are receiving a coupon, which means that we need to work with the various coupon and with the corresponding zeros. So what does that work for the 1.5? Well, our 1.5 is going to look something like this. We're going to have, and we assume they're all semi-annual, right? So it's going to be 1/2. So it's going to be 1/2 of a year. We're going to have 1 year, and then we're going to have 1.5 years. That's our 1.5 maturity, which is this one that we have over here. 1.5 maturity, that's what we're working with. It pays $8 coupon per year, right? But it's semi-annual. So what does that mean? 8% coupon per year, which means that for this first year we're gonna have 8%, but so that's gonna be $8. But the $8 is gonna be split between the first payment and the second payment. So ultimately, what we're gonna have for this coupon is gonna be $4 here and $4 here. For the last year, we're also going to get $4, but because we have a maturity this last period, we can add 100 there. So we're going to have essentially 104 for this last coupon. Now, the price of this bond, you remember what we did a little earlier. I'm going to go all the way back up here. To find the price of a bond, what we did was coupon multiplied by the exponential of the matching the 0 for the period for half a year, the same thing 0 for a year, and the same thing for the 0 for the 1.5 years. That's what we're going to apply here. So we go back to our table here, and what we're going to do is we're going to say price is going to be equal to, for present value, what is the 0 at half a year? It's that value here. So it's going to be 10.469 multiplied by half a year, so multiplied by 1/2, plus 4, which is that value, exponential of minus, what is the 0 in 1 year? The 0 in 1 year is 10.536. 10.536% plus 104 exponential of minus, what is the 0 at 1.5 years? We don't know. That's what we are after. That's what we are looking for. And so we're going to say RC, that's what we're looking for, raised to the power of, multiplied by 1.5, right? Raised to the power of 1 to 5. So that's what we have. And our goal is going to be to solve for this value. Now we know that this price is given to us. That price is essentially $96. And so we're going to say this has to be equal to $96. I think that's 96 even. There we go, $96. And so the way we're going to approach this is simply solve that for our realized compound yield for that period. So how do we do that? Well, we're simply going to do the following. We're simply going to say $96, which is our price, minus the first payment, $4, that is discounted at the compound yield for that maturity, which is 10.469% for half a year, minus the second one, which is $4, that is discounted at minus 10.536 for 1 year, multiplied by 1. All of that is going to be equal to the 104 multiplied by the exponential of minus our realized compound yield multiplied by 1.5. And so if we divide both sides by 104, we're essentially going to get rid of this term here. And then we take the log of both sides. So we're going to take the log of both sides. It's going to give us minus our realized compound yield multiplied by 1.5 is going to be equal to the log ratio. I'm going to call this whole thing, I'm going to call this whole term here, I'm going to call that B, the log of B, and I'm going to divide both sides by minus 1.5. So my realized my compound yield, or my zero here, is going to be equal to minus the log of B divided by 1.5. So let's compute B here. I'm going to do the following. I'm going to start with the first one. So it's going to be with this term that we have here. That term is 10, that's 10.536. That's the interest rate. I'm going to put a minus sign in front. I'm going to multiply that by 1, right? And I'm going to take the exponential of that. So second function exponential. That gives me that term there. I'm going to multiply that by 4 equal. And that gives me $3.6. So this here is going to be 3.6. Now I'm going to store that. So I'm going to say store that in the first memory slot. Store that in 1. Next, what I want to do is I want to do the second one. For the second one, I'm going to do 0.10469. That is the interest rate multiplied by 0.5 equal. That's that. I don't forget the negative sign there. And I take the exponential of that. That gives me 94.90%. I multiply that by 4 equal. That gives me 3.7960. So I'm going to store that in 2. So I'm going to store that in the second memory slot. So store that in the second memory slot. What do I need to do next? Next, what I want to do is the following. I'm going to get 96 minus my second memory slot. Remember, I stored this in 2 and I stored this in 1. So that's going to be 96 minus recall 2, which is that, minus recall 1 equal. That's going to be my numerator, and I'm going to divide that by 104 equal. That gives me that value, and that is going to be B, right? I'm going to take the log of B, so I press log of B. I'm going to multiply that by minus 1, so I remove the negative sign, and I divide that by 1.5. So divided by 1.5 equal. So that gives me 10.68%. So my zero rate with the maturity of 1.5 years is going to be 10.68%. So I'm going to do here 10.68%. That's my zero rate with the maturity of 1.5 years. Now, was that 10.60? Yes, 10.68%. The next measure is going to be for a zero rate with a maturity of 2 years, right? That's what we're looking for. Next is a zero with a maturity of 2 years. Now, for the zero with a maturity of 2 years, the process is going to be very similar. In this case, we're going to have 2 years, so I'm going to just draw the following: half a year, 1 year, 1.5 years, and then 2 years. I may be able to do this. There we go. What is the coupon payment? The coupon payment is equal to $12, and it's $12 for per year, and so that's going to be $12 per year. Remember, it says per year here, and we need to adjust that for a semi-annual period. So 12 per year, that's going to be equal to 6 for the semi-annual period. So we're going to have the following: we're going to have 6 here, 6 here, 6 there, and then remember we get face value, so it's going to be 106 there. Now we need to remember that the price is going to be equal to the present value of those at the various zeros. So our price, what is the price? Let's remember what the price is. That price is 101.6. That's 101.6. So we're going to go back in here. I'm going to say 101.6, which is our price, is equal to the present value of all of those at the corresponding zeros. So it's going to be 6 present value. What is the zero for half a year? The zero for half a year is going to be that zero that we had there, 10.469. So 10.469% multiplied by 1/2 plus 6 exponential of minus, what's the zero for 1 year? The zero for 1 year is that value at 10.536. So that's going to be 10.536% multiplied by 1 plus the third one is 6 multiplied by the exponential of minus. What is the zero for 1.5 years? That's what we just found, which is 10.68%. So 10.68% multiplied by 1.5. And the last one is a 0, is 106, which is that one, multiplied by the exponential of minus the 0 that we are after for 2 years multiplied by 2. So how do we solve for that? Well, I'm just going to write the formula here, or the expression here, and essentially what you're going to do is try to replicate what I had for the previous example, and then we're going to work it out together. So my 0 here is going to be equal to my price, which is 101.6, from which I'm going to subtract every single one of the other components. I'm going to start one after the other one, which is 6 exponential of minus 10.469 multiplied by 1/2 minus 6 exponential of minus 10.3536 multiplied by 1%. Remember, those are percentage. Minus 6 exponential of minus 10.68% multiplied by 1.5. And then I'm going to divide that by 106. That's going to give me the B that I had earlier. But then you remember that my answer was equal to the log of B. So it's going to be the log of this value minus that I'm going to divide now by 1.5. So I'm going to divide by T, 1 over T minus, and that's going to be my 0 right there. Now let's apply that. My 0 rate is therefore going to be equal to the following. I'm just going to use the calculator, and I'm going to do the same process. So I'm going to store this. I'm going to store this 0. So I'm going to be store 0, store 1. It's not store 0 here. I'm going to store this term 1. I'm going to store this term 2. And I'm going to store this term 3. I'm going to do 106 minus recall 1 minus recall 2 minus recall 3 divided by 101 minus recall 1 minus recall 2 minus recall 3 divided by 106. Take the log of that divided by t, and t is equal to 2 in this case, so we're going to divide that by 2 and take the negative sign of it. That's going to be our 0. So let me pull my financial calculator, and before I do that, I'm going to get into the memory. So I'm going to say second memory, and if I go through, I'm going to see that I have some data in memory. What I want to do is I want to clear that, so I'm doing the second clear work, and I go through it. I see that I have nothing in the memory, so I can get out of there and start my work. I'm going to do the first one, which is 0.10469. That's the interest rate, negative, multiply by 1/2, so multiply by 0.5 equal, and then I'm going to take the exponential of that, second function exponential, and I'm going to multiply that by 6. So multiply by 6 equal. So that gives me a present value of 5.690. My 5.690 is what I'm going to store 1. So I'm going to store 1. And I do the second one, which is 0.10536 negative, multiply by 1 equal, second function exponential. That gives me 0.9 multiplied by 6 equal. That gives me 5.40. I'm going to store that 2. So store 2. So I got the first one already, and I have the second one. Now I need to work on the third one. So for my third one, what I'm going to do is 0.1068, that's 10.6%, 68%, minus, multiply that by 1.5 equal, that gives me that value there, and I'm going to take the exponential of that, so second function exponential equal, that's going to be 0.85 multiplied by 6 equal 5.11. So the present value of 6 for 1.5 years at the 0 rate for 1.5 years is 5.11, and I'm going to store that 3. So store 3. So I stored that 3. Next, what I want to do is I want to say 101.6 minus recall 1 minus recall 2 minus recall 3 equal. That gives me the numerator. I'm going to divide that now by 106 equal. That gives me that value there. I'm going to take the log of that. And after I take the log of that, what I need to do is I need to remove the negative sign, and I need to divide that by 2. So that gives me 10.8% or 10.808%. So my realized or my compound yield for 2 years is 10.808%. And what I'm going to do is I'm going to go back up here, and I'm going to say, well, my yield for 2 years here is going to be 10.808%, and this is going to be my zero curve. So if I were to plot this, I would go ahead and say, well, what are those values? I have half a year, 1 year, 1.5 years, and 2 years. For these are going to be the zeros, and this is going to be the time. For half a year, what I have is, or I actually have a quarter of a year, so I have 2 years here. For a quarter of a year, so let's put 5.5, 1.5, and then 2. 4.25, I have 10.124, so it's going to be 10.124. Let's say it's about there. On the second one, I have 10.469, so I have 10.469, maybe a little bit above. The third one is going to be 10.536, so just a little bit above 10.536. The 1.5 years was 10.68%, so it's going to be just a little bit above again. And the 2 years we found at 10.808, so about there. So our zero would be something like this, where we would start about there, and then we would climb something like that. That would be our zero curve, and those numbers would be derived using the bootstrap method. Now let's go back to the slide, and that is essentially what we're going to do using this table here, using the price and using the method that we just described in order to derive the treasury zero curve. And the bootstrap method is essentially what we're going to be using. So an amount of 2.5 can be earned on the 97.5 during 3 months, and the 3-month rate is 4 times the the return, if you will, which is 10.256% with quarterly compounding. And then when you convert that to continuous compounding, that's what you get at 10.127. So that 10.127, if we go back to our curve here, was the 10.127 that we obtained here, right? So what the slide is showing is find the return on your investment over the zero, which gives you the compounding rate quarterly, and then you use that to find the continuously compounded rate. Ultimately, the method is the same with what we described on the board there, and to find the 1.5 years, you essentially solve this expression. That's a 4 and 104, and this is what we are looking for the 1.5 years. When we solve that for the 1.5 years, we get 10.68. So the 1.5 years, what did we get there? The 1.5 years, we get 10.68. There we go. That was 10.68 for the 1.5 years that we got. 10.681. And for the 2 years, if you did exactly what we did there, you would have 10.808. And so that is exactly what we have here, 10.808. And that's essentially our bootstrap. And the curve would look something like this. So our curve would be the connection of all of those. So this would be 0.25 at 10.127. The half a year at 10.469. The 1 year at 10.536. And the 1.5 years at 10.68. The 2 years will be at 10.808%, and those are going to be at 0 rate. Now with these data, we could then turn around and compute any bond prices that we would want to compute, no matter, even if we do not have the yield to maturity on the bond, because we can infer the present value of those coupon payment that we receive on the bond based on the 0 rate. Now we have some application of this on the OXI rate that we're going to see next. Now I understand this was a big chunk, so I'm going to stop the video here so that you get time to process this, and then we're going to come back in the next video and use applications and see applications of this zero curve to other concepts. All right, I'll see you in the next video.